Welcome back, guys. In this video we're discussing the remainder of the Taylor polynomial. In other words, the error associated with an approximation. In the last several videos, actually in pretty much all of the videos about power series and Taylor series, we've talked about taking a part of that Taylor series, just a truncated version of that, the partial sums of our Taylor series, those are Taylor polynomials, and using those to evaluate using those to approximate, the function. So that sounds like a good idea, and we drew some pictures and we said as long as we're near the center of the series, the Taylor polynomial is a good approximation of the function. But when I keep saying good approximation, you might be wondering to yourself, how good? How good is this approximation? What is the error associated with using that polynomial to approximate the function? And we can actually calculate that using Taylor's theorem. So here's Taylor's theorem. It tells us that if our function f has continuous derivatives all the way up to the n+1th derivative, so we get at least n+1 derivatives out of this, and these derivatives are all continuous on an interval I containing the center of the series. Well, in that case, then f can be written as its nth order Taylor polynomial, and that's just this. In expanded form, it looks complicated, but it's actually not. It's just the function value plus the derivative of the function at c times x minus c plus the second derivative of the function at c divided by 2 factorial times x minus c squared, and so on until you get to the nth derivative. So that's our Taylor polynomial, plus some error, or sometimes we call this the remainder of the polynomial, also known as the error term. And look at this. This is the form of the error term. It's not exactly the same as the next term in the series, but it's close. The next term in the series would have been the n+1th derivative evaluated at c over n+1 factorial times x minus c to the n+1. All I would do is replace the n's with n+1s. I go up to the next term. That's almost exactly what we see here, but instead of a c, we're evaluating this n+1th derivative at a, where a is some number between x and c. So x is the value where we are approximating our function. We're saying f of x is equal to this plus this remainder. So that remainder depends on x. And a is just some number between the x value where we're approximating the function and the center of the series c. Now, there are implications for this. I don't actually need to find the value of a. That's not our concern. What we really need to do is find an upper bound for this error. If I can find an upper bound for this expression, well, that's going to tell me the error, or the maximum error, in using this polynomial to approximate this function over here. So let's do some examples. And actually, let me write down that implication that I was talking about. If this is the form of the error, then the absolute value of the error, well, that has to be less than or equal to the maximum value of this. So this absolute value of x minus c to the n+1, well, it depends on whether that x minus c is positive or negative, so I can just put that in absolute value. n+1 factorial is always positive, so we don't need that absolute value there. But the absolute value of the error, the magnitude of the error, is always less than or equal to this times the maximum value of this. So that's the maximum value of the n+1th derivative at any x value between x, the value where we are approximating the function, and c, the center of the series. We want to find the maximum value of that. So if we can find a maximum value for that n+1th derivative on the interval from x to c, well, that's going to, if I multiply that by this, that will give me an upper bound for the error. So we need an upper bound for that n plus 1th derivative of x. And this is the maximum on the interval from a to x, or from x to, or not a to x, excuse me, c to x, or from x to c, depending on whether c is to the left or to the right of the x value where we're approximating our function. So let's work a couple of examples. On this one, we're asked to use Taylor's theorem to find an upper bound for the error of the approximation, and then we're asked to find the exact value of the error. So it looks like we've got arctangent, the arctangent function, and we want to approximate the arctangent function at x equals 0.04. And we want to use this third degree or third order Taylor polynomial to approximate the function. So one thing I like to do with all of these is I like to start by writing out the Taylor series first so that I can see the form that we're using to represent this function. So arctangent of x, remember that's the antiderivative of 1 over 1 plus x squared. And 1 over 1 plus x squared can be written as a geometric power series. So I'm replacing that negative, or that positive, with a minus like this. Instead of adding x squared, I'm subtracting a negative x squared. And I'm writing it in that form so I can identify a and I can identify r and write that expression as the series. We have a times r to the n. So I substitute in my a, I substitute in my r. I do a little bit of algebra. This is two factors. I've got a -1 as a factor and an x squared as a factor, so I'm going to apply that nth power to each of the factors separately. And x squared to the nth, because of this property right here from algebra, I can just multiply those exponents, that's x to the 2n, and we're anti-differentiating with respect to x. So the antiderivative of the sum is the sum of the antiderivatives, and we get x to the 2n plus 1 over 2n plus 1 plus a constant c, but when I substitute in x equals 0 to this side and to this side, I get arctangent of 0 as the sum of infinitely many zeros plus c. So we see that c must be 0. And we've got this Taylor series, or we've got a series representing our arctangent function. And this power series representing the arctangent function is the same as the Taylor series, because we know that this function this series converges to this function on the interval where this is well defined. So this series converges to this function when the absolute value of x is less than 1. And I believe in another video we showed that it also converges at -1 and 1. So arctangent can be written this way. And so we can think of the partial sums of this series as good approximations to the function arctangent of x, as long as we stay near the center, which is x equals 0. So arctangent of x, well, it can be rewritten this way. If I expand the series, I get when n equals 0, -1 to the 0 is 1. That's x to the 0 plus 1, so x over 1. So we just get an x. And then when n equals 1, we get a minus because that's an alternating term, an alternating factor. If n is 1, well, that's just an odd number, so that's going to be x cubed. 2 times 1 plus 1 is 3, so we've got x cubed over 3. And notice the pattern. I have odd numbers here and the exact same odd number in the denominator, and then it's alternating. So I'll get minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and the pattern continues. So that's our power series for arctangent of x, and we've got various Taylor polynomials or Maclaurin polynomials for this. So we could use p sub 0 of x, that's the 0th order polynomial, equals 0 to approximate arctan. Or we could use p sub 1 of x, and since there's no x squared term, that's also the same as p sub 2 of x. That's just x. That's the tangent line. Or p sub 3 and p sub 4. Those go all the way up to the x to the 4th term, so that's x minus x cubed over 3, and so on. So now let's look at our original question. This pattern continues. It's asking us to use Taylor's theorem to find an upper bound for the error of the approximation and then calculate the exact value of the error. So they're giving us x equals 0.4. Okay, that's good. And notice that we're using a 3rd degree polynomial over here. So we're actually using this. We're using the 3rd degree Taylor polynomial or Maclaurin polynomial, which is the same as the 4th degree Taylor polynomial or Maclaurin polynomial. It's this guy. So we're using this to approximate our arctangent function at x equals 0.4. So I'll write down my x value. X equals 0.4. And then I will write down the formula for my remainder term, because the question asks us to use Taylor's theorem to find an upper bound for the error of the approximation. So here's our error of the approximation. And this time, they're giving us a 3rd degree polynomial. They're using this to approximate the function. But p sub 3 and p sub 4 are the same. So the error for that 3rd degree polynomial or 3rd order Maclaurin polynomial is the same as the error for the 4th order Maclaurin polynomial. And we know the error for the 4th order Maclaurin polynomial is this. It's the 5th derivative of the function evaluated at some x value. We're going to call it a, all divided by 5 factorial times x minus the center of the series, and this is centered at 0, all raised to the nth power, excuse me, not nth power. If this is 5, that's going to be 5th power right here. Okay. So the absolute value of the error at x equals 0.4 is going to be equal to this. It's the absolute value of the 5th derivative of the function evaluated at some number a, where a is a number between x equals 0.4 and the center of the series, times, I'm replacing x with 0.4 to the 5th, divided by 5 factorial. So I've got 0.4 to the 5th, 5 factorial, those are known, times the absolute value of the 5th derivative of this function, evaluated at x equals a, where a is some number between the center of the series and the center of the series that we're using the polynomial to approximate it from. That center is 0. and the x value that they gave us. The x value was 0.4. Okay, so what I really need here is a maximum value of this fifth derivative. I need the maximum value of the fifth derivative of this function, the maximum of the absolute value of the fifth derivative of the function on the interval from 0 to 0.4. That's going to be an upper bound for our error, because this is just the fifth derivative of the function evaluated at some number between 0 and 0.4. So this will be less than or equal to this number times this number times the maximum value of the absolute value of the fifth derivative of x on the interval from 0 to 0.4. So it looks like we're going to have to find the fifth derivative and then find the maximum value of that fifth derivative on the interval from 0 to 0.4. So okay, we can do that. F of x is arctan of x, and the first derivative is just 1 over 1 plus x squared. Now I need the fifth derivative. So I will rewrite this as 1 plus x squared to the negative 1, and then we'll use the chain rule to take the next derivative. So the derivative of something to the negative 1 is negative 1 times the function that we started with to the negative 2 power times the derivative of the inside by the chain rule. Derivative of the inside is just 2x. And I could rewrite that this way. This is negative 2x all over x squared, or 1 plus x squared quantity squared. That's the second derivative. I need the fifth derivative, so we got to take the derivative again. This time it makes sense to use the quotient rule because that numerator has an x in it. So we'll go back to Calc 1. The derivative of one function divided by another function is the bottom function. Remember that low d high minus high d low over low low mnemonic? That's exactly what we're using here. So I have the bottom function times the derivative of the top function. That's low d high. The derivative of the top function is negative 2. Minus high. So I'm subtracting the negative 2x. Times the derivative of the low function. Well, I'm going to have to use the chain rule for that because I've got a function squared. The derivative of a function squared is 2 times the function times the derivative of the inside by the chain rule. The derivative of 1 plus x squared is 2x. So that's our low d high minus high d low over low low. I'm taking this, it's squared. When I square it again, it's going to be raised to the 4th. Okay. Now this can be simplified a little bit, so let's simplify where we can. I see that I have a 1 plus x squared and a 1 plus x squared in both of these terms. I also have a negative 2 in this term and a negative 2 in that term. So let's factor out a negative 2 times 1 plus x squared. Now in the numerator, I'll have this times another 1 plus x squared would give me that first term. And then I have to ask myself, this times what would give me the second term? Well, I factored out a negative 2, and I factored out a 1 plus x squared. So I'm still left with a negative and an x here, and a 2 here, and a 2 here, and an x here. So that's going to be 4x squared times, well, 1 plus x squared we already got rid of, isn't that right? So I've got a negative times a negative is a positive 2. That's 2 times 2 times 2, that's 8x squared times 1 plus x squared. So negative 2 times that. Oops, I think that's supposed to be negative. All right. So I've got negative 2 times 1 plus x squared. And then this simplifies to the x squared minus the 4x squared is negative 3x squared. Just doing some algebra. Nothing fancy. And one of those will reduce. So we end up with this. negative 2 times the quantity 1 minus 3x squared all over 1 plus x squared quantity cubed. That's the third derivative. We've got 2 more derivatives to take. It's sort of tedious, but that's okay. We can do it. Trying to find the fifth derivative. And then we're going to maximize that fifth derivative. So we'll find the fourth derivative next. And for that, I think it will be simpler if we distribute the negative 2 back in. So we'll have a negative 2 plus 6x squared in the numerator, all over 1 plus x squared, quantity cubed. And we're taking the derivative using the quotient rule again. So we've got low, bottom function, d high, the derivative of the top function is just a 12x, minus high, so minus that top function, over d low, that requires the chain rule. Derivative of something cubed is 3 times whatever we started with, squared, times the derivative of the inside, which is a 2x, all over the bottom function squared. So I've got something cubed and you square it, so you're going to multiply the 2 and the 3 to get a 6th power there. Alright, so we want to simplify this as well. I've got a 1x squared here and a 1x squared, or 1 plus x squared here and a 1 plus x squared there. We can simplify that. Also see a 6x as a factor here and a 12x there. I think I'll rewrite this a little bit first. If I distribute that negative, I'll have a 2 minus 6x squared. 3 times the 2x gives me a 6x. And then I have a 1 plus x squared quantity squared. And I could actually factor out a 2 from this as well. So 2 times that 6x will give me a 12x. And then I have a 1 plus 3x, or a 1 minus 3x squared, times this. It's just algebra. It's a little tedious, but that's okay. These have a 12x in common, and they also have a 1 plus x squared quantity squared in common. So then I ask myself, this times what gives me my first term? Well, I guess I'm missing the extra 1 plus x squared, so I write that in here. And then I say to myself, this times what gives me this second term? Well, the only thing that's missing is the 1 plus negative 3x squared. Or 1 minus 3x squared, same thing. So these guys reduce with 2 of these guys. And now I've got a 12x times the quantity 2. X squared minus 3x squared is negative 2x squared. Okay, and we could factor out a 2 from that as well. So I've got 24x times 1 minus x squared all over this. And I would stop there if I just wanted to find that fourth derivative, but I want the fifth derivative, so actually I think it makes more sense to distribute. I have 24x minus 24x cubed in the numerator. If I leave it in that form, it'll be easier to take the fifth derivative. So we'll take the fifth derivative now. Using the quotient rule again, it's the bottom function times the derivative of the top function. So we get 24 minus, that's 24 times 3, that's 72 times x squared. So that's low d high minus high d low. Use the chain rule, so we have 4 times 1 plus x squared cubed times the derivative of the inside, which is just a 2x. So we have low d high minus high d low all over low low. If I take something raised to the 4th and I square it, I get that something raised to the 8th. Okay, and then we want to simplify as much as we can. Notice that these two have a 24 in common, so we can factor that out. Got a 24 times 1 plus x squared to the 4th, and when I factor out a 24 there, I'm left with 1 minus 3x squared. Over here, I can factor out a 24x, and I'm left with 1 minus x squared. The 4x times the 2x is an 8x. And I've got 1 plus x squared quantity cubed there, all over this. Okay. We're still simplifying. We're looking at this term and this term. Well, they have some things in common, so we'll factor those out. They both have a 24. And this is a 1 plus x squared to the 4th, and that's a 1 plus x squared cubed, so we'll factor out a 1 plus x squared cubed. And we'll see what's left over. This times another 1 plus x squared times a 1 minus 3x squared gives us our first term. And this times what over here? Well, I'm missing a negative, and the 24 is taken care of. I need the x. Then I've got the 1 minus x squared factor, and then the 8x factor. Okay. Yes, very tedious. Lots of derivatives. That's okay. So we've got 24 times the quantity 1 plus x squared quantity cubed, and then over here I'm going to distribute. First times first is 1, outer times outer is minus 3x squared, inner times inner is x squared. Last times last is negative 3x to the 4th. And then over here I've got a negative 8x times x, so that's negative 8x squared, times this quantity 1 minus x squared. So we'll have to distribute that and collect like terms there as well. Those 3 are going to cancel with 3 of those, so we'll have a 1 plus x squared to the 5th in the denominator. And this will simplify to a 1 minus 2x squared minus 3x to the 4th. And if I distribute the negative 8x squared, I get this. Didn't realize there was so much algebra, but I guess there is. There's a lot on this one. That's okay. So I've got an 8x to the 4th minus 3x to the 4th is 5x to the 4th. Negative 2x squared minus 8x squared is negative 10x squared plus a 1 all over this. Okay. Now the question said, hard to remember because we've been taking derivatives for so long. We're trying to find an upper bound for this error, and we're using a third order Taylor polynomial, Maclaurin polynomial, to approximate the arctangent function at x equals 0.4. So we said this is what the error looks like, and remember a is just some number between the x value where we're evaluating the function, 0.4, and the center of the series. The center was 0. So what we really need is a maximum value for this fifth derivative, or the absolute value of this fifth derivative, on the interval from 0 to 0.4. So we needed to find that function and then optimize it. We need to find the maximum value of this function on this interval. So that's the function we need to maximize on the interval from 0 to 0.4. Now in order to maximize it, guess what we have to do? Remember extreme value theorem from Calculus 1? We have to find the value of the function at the endpoints. At x equals 0, we get 24. At x equals 0.4, let's see what we get. So 5 times 0.4 to the 4th minus 10 times 0.4 squared plus 1 times 24 divided by, open parentheses, 1 plus 0.4 squared, close parentheses, raise that to the 5th. And so that is approximately negative 5.393. Okay. So the extreme values, or the maximum value of the absolute value of this function, might occur here or here, and it may also occur on the interior of this interval, some number between 0 and 0.4. So to figure out whether or not we've got a critical point, or whether we have a maximum value on the interior, we've got to find the critical points of this function on the interval from 0 to 0.4. So we need to compute the 6th derivative, which is a lot, but it's just one more derivative, no big deal. Nothing we can't handle. And just to make my life a tiny hair simpler, I'm going to factor out that 24. So according to the quotient rule, we have the bottom function times the derivative of the top function, and I've factored out the 24. So the derivative of the top function is 20x cubed minus 20x. Derivative of 1 is 0, so that's low d high minus high. D low, the derivative of the bottom function, is 5 times the quantity 1 plus x squared to the 4th times the derivative of the inside, which is 2x, all over the bottom function squared. So I've got 1 plus x squared to the 5th, and I square it, so that means I'm multiplying that exponent by 2, so I get 10. Alright, so what do all these have in common? Well, on this one, that factor, or that term, excuse me, I can factor out a 20x from those two terms. So I've got a 20x. 20x times x squared gives me the first term. 20x times negative 1 gives me the second. Over here, I see a 10x that I can pull out front. So I have a 10x times this polynomial. And we still have the 1 plus x squared to the 4th, all over 1 plus x squared to the 10th. Now, if I'm looking at this as one term and this as another term, I see that they both have a 10x in common, and this has an x squared, or 1 plus x squared to the 5th, and this has a 1 plus x squared to the 4th, so I can factor out the 1 plus x squared to the 4th from both of those. So I'm factoring out the 10x. Let's take that 10x and multiply by the 24 now. So we have 240x and a 1 plus x squared to the 4th, all divided by 1 plus x squared to the 10th. And we say to ourselves, this times what gives me my first term? Well, we factored out a 10x from this, so we're still left with a 2 there. And we still have one of those 1 plus x squareds, and then we have an x squared minus 1 there as well. That times that would give me that. And we factored out the 10x. We factored out the 1 plus x squared to the 4th. So all that's left is that negative 1 times that polynomial. I'll distribute that negative now. Okay. And let's do a little algebra. I've got 2 times this product. First times first is x squared, outer times outer is -1, inner times inner is x to the 4th, and last times last is minus x squared, so those reduce. And 4 of these reduce with 4 of those, so we're going to have a 1 plus x squared to the 6th in the denominator. And then we'll have 2 times x to the 4th minus 2 minus 5x to the 4th plus 10x squared minus 1. And that simplifies a little bit further. My goodness. I picked out this problem, but I had no idea it was going to be so complicated. That's okay. We can do it. It's not actually that difficult, it's just tedious. So I've got 2x to the 4th minus 5x to the 4th is -3x to the 4th. And then I've got a 10x squared and a minus 3, all times this. Okay. This is the 6th derivative of f. Now to see if, to find the critical values of the 5th derivative of f, I need to take its derivative, that's the 6th derivative, set that equal to 0, and then solve for x. Now if I set this equal to 0, the only way that's 0 is if the numerator is 0. And we're looking for this derivative to be 0 on the interval from 0 to 0.4, not including 0, not including 0.4. So this times this is 0 when this is 0, or this is 0, but we're not interested in when this is 0, because when x equals 0, we already tested that. So the only other possibility is that we've got -3x to the 4th plus 10x squared minus 3 is 0. Let's divide everything by -3. I know it looks bad, but it'll make it a little bit easier for us to solve this for x. Okay. I'm trying to find the x values that make this 0. Well, I think I can complete the square on this. So this is my b. Take half of b and square it. So it gives me 25 over 9. That's what I need to make this a perfect square. So let's subtract the 1 from both sides. And then we'll have x squared minus 10 over 3, or x to the 4th, minus 10 over 3 times x squared equals -1. And we're going to add 25 over 9 to both sides. And then this is x squared minus 5 over 3 quantity squared. And this is a -9 over 9 plus 25 over 9. So we get 16 over 9. Okay. Getting closer. So if I've got x squared minus 5 over 3 squared equals 16 over 9, take the square root of both sides. Don't forget your plus or minus. We have x squared minus 5 over 3 is plus or minus 4 over 3. So we'll add the 5 over 3 to both sides, and we'll get x squared equals -4 over 3 plus 5 over 3. That's one possibility. Or x squared equals positive 4 over 3 plus 5 over 3. So here I get x squared equals 1/3, so x equals 1 over the square root of 3. Well, plus or minus 1 over the square root of 3. And then on this one we get x squared equals 9, or excuse me, 9 over 3. So x squared equals 3. So x equals the square root of 3. Now we're only interested in the x values on this interval 0 to 0.4 from before. Square root of 3 is obviously greater than square root of 1. So this is not on our interval, so that's not our concern. That 1 over square root of 3, not the negative one, but the positive one, that might be on our interval. Oh, it's not. It's not on the interval. So we don't have any critical values on the interval. There's a lot of work just to find out there are no critical values. So what are we doing again? Oh yeah, we're trying to maximize. We're trying to find the maximum value of this function. Well, it looks like the maximum value occurs at 0, and it's 24. So the maximum value of the absolute value of the fifth derivative on the interval from 0 to 0.4 is equal to 24. Okay, now let's go back to the original problem that had to do with error. A lot of calculations. It's okay. Lots of good opportunities to review. All right, so we're right here. We're trying to find an upper bound for the error. So this is 0.4 to the fifth, and the maximum value of that is 24, and we're dividing by 5 factorial. And 5 factorial actually has a 24 in it, doesn't it? It's 5 times 4 times 3 times 2. So we end up with 0.4 to the fifth over 5. So the maximum value of the error is that to the fifth divided by 5. It's actually pretty tiny, 0.002048. So the maximum that we could be off is 0.002048. And let's go back to the original question. Say maximum that we could be off by what? How are we approximating function? What were we talking about again? Okay. Question said, use Taylor's theorem to find an upper bound for the error of the approximation. So we're saying we're going to use this to approximate arctan of 0.4. According to our calculations, the maximum value of the error was 0.4 to the fifth times the maximum value of the fifth derivative on that interval, which was 24, divided by 5 factorial, which is approximately 0.002048. And then the question says, find the exact value of the error. Say, okay, well, the exact value of the error is going to be the difference between the function value at 0.4 and the approximate value at 0.4. So let's find the function value at 0.4 and the approximation at 0.4. And we were using the third degree polynomial, which is the same as the fourth order polynomial. Oops, that's a different problem. Okay. So this is easy enough. Let's find arctan of 0.4 using our calculators. Make sure your calculator is in radian mode because your arctangent function, inverse tangent, is going to return an angle. You don't want that angle in degrees, you want it in radians. So according to my calculator, arctangent is approximately, or arctangent of 0.4 is approximately 0.3805, and the polynomial approximation, it's the third order or third degree Maclaurin polynomial, which happens to be the same as the fourth order polynomial. So that's 0.4 minus 0.4 cubed, all divided by 3. And let's do the math. We do 0.4 minus 0.4 cubed, all over 3. And we get 0.3786 repeating. So I'm going to do this minus that. Actually, I think I'm just going to do arctan of 0.4 minus the last answer. And let's see what it says. Okay, so it says exact error. We want the exact error, but all we can get is the approximation, as good as our calculator can give us. And it turns out that that's approximately 0.0018, let's say 40 if I round. So our formula told us that the maximum value of the error would be 0.002. It turned out that the true error was 0.0018. Not bad. It was a pretty good approximation. Okay, so that's it for this video. I know that was a long and involved process. The reason why it was so involved was because we had to find the fifth derivative of this function, and then we needed to maximize it on the interval from 0 to 0.4. So that took a lot of work, and there were a lot of quotient rules involved. But really, it comes down to evaluating this. We had to identify the x value, which was 0.4. Then we already know what the center is, so we just did 0.4 to the n plus 1 power. And we're not using the n literally, like this is n equals 3. We ended up using a 5 here instead of a 4. And the reason for that is because the error in using the third degree Taylor polynomial, or third order Taylor polynomial, was the same as the error in using the fourth order Taylor polynomial, because we only have the odd terms here. So we actually had to go all the way out to a fifth power here. So we had the 0.4 to the fifth, we had the 5 factorial down here, and then we had to maximize the fifth derivative on this interval, starting at 0 and going to the value of the x, or the x value that they gave us. So we had to maximize this function on the interval from 0 to 0.4. And that required using the extreme value theorem from Calculus 1. And then it turned out that it was at one of the endpoints after all. The absolute max was at one of the endpoints. But that's okay. Once we found the maximum value of that derivative on that interval, we just plug that in right here, and we use a calculator to approximate it. And then we saw that the true error was 0.0018 approximately. The maximum error is a pretty good estimate of the true error. So that was pretty good. That means using this is a good idea for approximating this function. We can be sure that we're right to within 0.002 units.